If you've ever been to the Saddledome, you know there's 3 levels that you can sit on to watch a hockey game. You can be on level 1, level 2, or level 3. You can't just be anywhere. Neither can electrons as they orbit around the nucleus. They have to sit on level 1 or level 2 or level 3 or level 4 or whatever. They can't just be wherever they want, like Rutherford said. Now, when I go to the Saddledome to watch a hockey game, I know that I have to be on one particular level, right? I know that each of those levels is characterized by a specific energy as well. If you've been there, you know that the first level tends to be a little bit more subdued. That tends to be the people that maybe have a little bit more cash. Maybe they came from work downtown. Maybe they're still dressed in their dress clothes from work, right? They cheer, but they're not quite as loud as the second deck and the third deck. The energy at that first level is characterized, that first level is characterized by a specific energy on average. So the people in the Saddledome have to sit on a particular level, and the energy of each level, or each level is characterized by a specific amount of energy. The first level has, it's kind of a little bit lower energy. The second level, that's kind of the average person maybe. Okay, average person where, maybe someone's had a couple beers. Okay, they're cheering, whatever, they're excited. But it's not like that third level, the sport check zone. If you ever sat up there, that is definitely characterized by a lot more energy than the other 2 levels. Right? I sat up in the sport check zone one time with Mr. Kruger years ago. I can't remember who the Flames were playing. Let me just tell you that it was not the Saskatchewan Roughriders. Wrong sport. But 2 guys in the same row as us were dressed up all in green and white with their faces painted green and white, yelling, "Go Riders, go!" the entire game. When you go to a hockey game, you have to be on a specific level, and each level is characterized by a specific amount of energy. Well, Bohr said the same thing about electrons as they orbit around the nucleus. Yes, they orbit around the nucleus, but they can't just orbit wherever they want. They have to orbit on a specific level. Now, each level, just like the Saddledome, is characterized by a specific amount of energy. Now, this might be a little bit more detailed than you need to know. But if you take chemistry, you already know this, right? Not only is each level characterized by a specific amount of energy, we know that each level contains a certain amount of electrons, right? 2 electrons on the first level, up to 8 electrons on the second level, and so on. You don't need to know those numbers for sure. But you think about the analogy that we use with the Saddledome, that holds as well, right? The first level holds, say up to 7,000 people. The second level holds up to, 8,000 people, let's say. What happens if there's a few vacancies down on the first level? There's empty seats down there? People move down. What do? You fill up those lower levels first. There's a maximum number that you can have in each level, and we always want to fill up those lower levels first, which is exactly what happens with the Bohr model of the atom as well, right? We have levels. Each level is characterized by a specific amount of energy, and then beyond that, we could say that there's a certain number of electrons that could exist, and we all in each level, and we would fill up those lower levels first. Now, next aspect of the Bohr model of the atom that separates it from the Rutherford planetary model of the atom. Let's swing my keys around my head here, okay? The keys represent the electron, and my hand that's in the middle that's holding the string here represents the nucleus. As this electron orbits around the nucleus, it's going at a constant speed, right? It's not speeding up or slowing down, but it is accelerating. It is accelerating. What type of acceleration does it experience when it goes in a circle, yet at a constant speed? Yeah, it's a centripetal acceleration. If you think back to the very beginning of our last unit, EMR, James Clerk Maxwell said that accelerating charges, he didn't say charges speeding up. He said accelerating charges. This is acceleration, right? Accelerating charges generate EMR. But these electrons, as they orbit around the nucleus, they don't emit EMR. We know that. Because if they did, Think about this. This electron that's orbiting around right now, these keys that are circling around right now, if they did emit EMR, what would happen to it? Yep. Yes. Yes. We do get EMR from the atom, so that's not a way for us to distinguish exactly where the EMR is coming from. Think about this though. If these electrons were orbiting around the nucleus and they gave off EMR, they gave off energy, then they would lose energy. And if they lost energy, they would slow down. And if the electrons slow down, they would spiral into the nucleus like my keys just did. In other words, we wouldn't have any chemistry because the electrons wouldn't be doing what they do. And if we didn't have chemistry, we certainly wouldn't have biology. And if we didn't have biology, we wouldn't be talking about this right now. This doesn't happen. Maxwell predicted that it should happen, but it doesn't. There's something up here. It's as if these electrons, as they orbit around the nucleus, don't accelerate. In fact, it's as if they don't even move. It's as if they're stationary. We call it a stationary state. They should emit EMR, but they don't. If they did, the electrons would spiral into the nucleus, and life as we know it, matter as we know it, the universe as we know it wouldn't exist. It's amazing, isn't it, how all these different conditions that must be in order for the universe and for life to exist, it just happen to be perfect. Like the probability of everything being the way it is in order to cause life to form as it did is like one in infinite almost. Almost like it was some guiding principle. Or almost like it was some guiding force behind it. Now, the third aspect to the Bohr model of the atom talks about when EMR is produced, right? EMR isn't produced by electrons orbiting around the nucleus, but we do get EMR from the atom. We get EMR from the atom when we have transitions of electrons. If I'm on the third level of the saddle, this is what I used to do when I was young and poor, as opposed to like I am now, which is old and poor. I used to sit up in the third deck. When I moved to Alberta in 1995, it used to cost $8 for the third deck in the Saddle Dome. A movie was $9. It was cheaper to go to a Flames game than it was to go to a movie at the time. So I used to go to a whole bunch of them. And at that time, you might get 14,000 people at a game. There's all kinds of empty seats. So you go spend $8 and sit in the sport check zone. And then you look at these seats down there, and it's like, oh, nobody sat in those for the entire first period, so what do? Well, when there's a vacancy, you move down. Right? You move down into a lower seat. Well, that's what electrons do as well. If the electrons are in the third level, but there's only one electron in the first level, and there's space for two, the electron moves down, says, oh, there's a seat down there right next to the glass. Why wouldn't I move down? Electrons can fall to a lower level where they give off energy. But on the same token, they can also jump to a higher level. Okay, when I used to go to those games, I'd sit up in the third deck of the Saddle Dome. I'd go there, you come in on the first level, and then you have to climb all of these stairs. Like, man, you better have your Starbucks extra caffeine, mocha, frappo, whatever, chino, in order to get the energy, to absorb the energy to go to that third deck. I've sat literally in the top seat, the highest seat that exists in the Saddle Dome. And it takes you need to absorb a lot of energy to go to that higher level. Now, on the same token, right, when you go to a lower level, you're going to give off energy. That's when you give off the photon. So we can make transitions from one level to another, two types. We can jump to a higher level, rise to a higher level by absorbing energy, That energy could be in a number of forms. Usually it's EMR, but it could be something collides with an electron and gives it energy, or it could be some kind of electrical energy, usually photon energy. If light gets passed through a cold gas, that cold gas can absorb some of those photons and cause the electrons to jump to a higher level. But then that leaves a vacancy. Somebody went from the first deck up to the second deck, and somebody in the third deck says, hey, there's an empty seat. I'm going to move down to the first deck. So the electrons can also fall to a lower level, and when they do, they give off energy, specifically EMR. So to jump to a higher level, they absorb energy. Usually that's going to be EMR, photon. When they fall to a lower level, they give off energy, and it will always be EMR. All right, so how do we graphically represent number 3? How do we graphically represent these transitions? Well, we usually call an electron level diagram. This one is unique to hydrogen. The diagram looks remarkably similar to this, though, for other elements as well, except the numbers on the left-hand side. Please don't copy this down. You have this copied down already on your very last worksheet. I gave you a copy of this on your worksheet. So everything that I write down here, you can feel free to just do it on your worksheet, okay? Rather than copy this down again. So this electron level diagram shows all the possible levels that electrons can be on for hydrogen, right? Every element is different. This is for hydrogen. Now some of you are like, well, wait a second, there's only one electron in hydrogen. Yeah, there is. But that electron can be on all kinds of different levels depending upon the energy that it's received or given off. This down here would represent the nucleus. That doesn't form part of the electron level diagram, but I just want you to understand that the ground state, or the n is equal to 1 level, is the level that is closest to the nucleus. And then every level above that is what we call an excited state. The electron should be in the ground state, but if it's received some energy, if it's had that mocha frappa, whatever from Starbucks with all the caffeine, then it's in an excited state. It's going to a higher level, temporarily. It doesn't want to stay there, because there's an open level in the ground state now, but it'll be there for at least a little while, right? Now, a couple things that I want you to notice about this diagram. First of all, the spacing between the levels is not equal. You can see that the further up you go, the closer the levels get to each other. That's because the energies of the levels, the energy of each level gets progressively closer as we go up. Right? The difference between level 1 and level 2 is over 10 electron volts. Between level 2 and level 3 is less than 2 electron volts. So as you go further and further up, the spacing gets closer and closer together. Now the second thing I want you to recognize is that I've only got 6 levels labeled here. This keeps going, 6, 7, 8, 9, 10. But as you can imagine, kind of run out of space there, right? I got nowhere else to write in the 7th and 8th and 9th and 10th level, because they're getting too close together. But we get the idea. The third thing that I want you to recognize is that this dotted line at the top isn't really a level. This is where the electron has left the atom. Right? It's gone out of the atom. It's the infinite level. It's when the electron is free. It's not excited. It's gone. And the last thing I want you to recognize, the second to last thing that I want you to recognize, is that the energies along the side here, which distinguish the hydrogen electron level diagram from other ones, these energies that are on the side here are A, negative, not positive, and B, they get bigger as we get closer to the nucleus. Now, why are they negative? Because these things represent potential energy. I'll give you an analogy here. Adam, what is your potential energy right now relative to the ground you're standing on or sitting on? 0. Atom's gravitational potential energy relative to the ground is 0. If you were to climb up a ladder, Adam, your potential energy would become 100,000, depending on how high you went, right? But if you were to dig a hole down into the earth and use the ground as your reference point, go down that ladder into the ground, your energy would become negative because you'd have a negative height. The electron on the infinite level has an energy of 0. We define that. They were defining it relative to where the electron has left the atom. When atom is on the surface of the earth. As Adam digs the hole and goes down into the earth, closer to the core of the earth, not only does his energy become negative, but it becomes bigger negative, just like this. Right? Now, you're going to get on your final exam next Thursday a question like this, except it's not going to be hydrogen. But don't worry about that. The only difference is the numbers along the side. We're going to do the same thing with it, just with different numbers along the side. So one more thing that I should have mentioned here. All of these lines represent possible transitions when electrons are going from high to low level. We can just as easily have transitions going this way. These are transitions where the electrons have absorbed energy to go to a higher level. Make sense? All right, we're going to do a few examples, and that's going to be it for us. First question, example number 1 that's in. Example number 1 says, how much energy is emitted when an electron makes a transition from 3 to 1? How much energy is emitted when we make a transition from 3 to 1? If we went from 1 to 3, we would be absorbing. From 3 to 1, we emit. How much energy is emitted? Let's go back to our diagram. How much energy is emitted when we go from 3 to 1? Listen, let's draw that out here. Let's draw it there from 3 to 1. It's that transition right there. All we're going to do to find the energy that's emitted is subtract the energies here. The difference in energy between the two levels. It's the first energy level minus the third energy level. How do we know it's E1 minus E3 rather than the other way around? Yeah, final minus initial. So E1, be careful here, is negative 13.6, not 13.6, negative. Subtract, E3 is negative 1.51. That gives us negative 12.09 or negative 12.1 electron volts. That's the energy of the transition, negative 12.1. It's always going to be negative when you give off energy, when you emit energy, positive when you absorb. But if you lose a negative somewhere in there, I'm not too worried about that. As long as you get the magnitude of it, that's what I care about. So you made that positive 12, that's fine. You're not going to get a question on the test where option A is negative 12.1 and option B is positive 12.1. But that won't happen. The difference in energy, 12.1 eV, the energy that's given off. Now, number 2. What's number 2 ask us? The electron on the first level absorbs 12. To what level does it rise? Actually, let's make it 12.1. It absorbs 12.1. To what level does it rise? Well, if we're on the first level and we absorb 12.1, that's going to take, isn't that going to take us to level 3? Right? We're going to say negative 13.6. We absorb 12. That takes me to negative 1.6. Is that right? Yeah. Actually, let's change that number a little bit. Something. You guys see the problem with this? If we get to negative 1.6, what level does it go to? Oh man, it's so close to level 3, isn't it? Where would it go to? Oh. Yeah, level 2. Yeah. Like I go to 7-Eleven for a Slurpee, a large Slurpee, it costs $2.50. Medium, by the way, is $2. I go in there with $2.45. What do I come out with? A medium. I got way more than enough for a medium. But I don't have enough for a large. Right? So here's the money I go into 7-Eleven with. Oh, I'm so close to having enough for a large Slurpee. I got way more than enough for a medium. But I don't have enough for a large. So what do I come out with? Medium. So we would say to negative 1.6, therefore, it would go to the second level. Even though it's so close to the third level, it would only go to the second level. Speaking of so close, we are so close to being done here. Third question says, determine how much energy needs to be absorbed when an electron goes from second to fourth level, and what's the frequency and wavelength of it. From the second to fourth level. Let's draw that one. From the second level to the fourth level. The fourth level is negative 0.85. And the second level is negative 3.4. Subtract negative 3.4 gives me 2.55. Is that right? You notice something with all three of these questions? Notice in all three questions we've used not this energy or this energy, but the difference between the two. You'll never do a calculation in physics 30 with just one of those energies. It's always with the difference. Always with the difference. Let's find the frequency. That's easy. Look. E is equal to h times f. The energy is 2.55 EVs over, let's use Planck's constant of 4.14 because we're in EVs here. I forgot my calculator's busted again. Let's figure out what that is. 2.55 divided by 4.14 times 10 to the negative 15, 6.16. That sound like a reasonable number? Yeah, that's visible light, right? Remember back in last unit, very first day, we looked at how each type was produced. Radio waves and microwaves were produced by oscillating charge. Gamma rays, nuclear decay. X-rays were rapid deceleration of electrons. Infrared, visible light, and ultraviolet were produced by transitions of electrons from high levels to low levels. That's visible light. That question, by the way, also asked me for the wavelength. So let's find the wavelength. The energy of the transition, not the energy of a level, the energy of the transition. Gives me 4.87 times 10 to the negative 7 meters. So we have to absorb 2.55 eVs, and that can come from a lot of different places. But if it comes from light, photons, the frequency of that photon would be 6.16, and its wavelength would be 4.87. One more example, and it's a pretty straightforward one, easier than this one. All right, last question here. That's our last example question of the year, actually. And it's a nice, easy one, too. What's the ionization energy for an electron in the first level of hydrogen? How much energy is required to ionize this electron? How much energy is required to get this electron out of the atom when it's in the first level? Here, I'm going to erase some stuff, so we've got more space to work here. Why isn't this erasing for me here? Well, it erases this way, I guess. All right, so we want to go from the first level to the infinite level. We're going to say delta E is the final minus initial. It's 0 eV, because that's when it's left the atom. That's when atom is on the surface of the Earth, right? Out of the Earth. Subtract the initial is 13.6, negative 13.6. So the ionization energy is 13.6. Electron. That's how much it takes to get the electron out of the atom. We could find the frequency of that, HF, the wavelength, hc over lambda. All 4 questions, notice, all 4 questions. Not once have we used one energy level. Every single time, what have we done? We found the difference in levels. Sometimes you're given the energy of the transition, the difference already. If you're not, then you got to subtract the levels to find it. Josh, question?
What happens if you put more energy?
If it would absorb more than 13.6 electron volts, it can't do more than leave the atom. It would just be moving faster. Okay? Like, essentially, you exceed the work function. Right? All right. I would like you to take a look at worksheet number 26, the very last one in the worksheet booklet. And I would like you to do in worksheet number 26 the following questions. Number 1, number 3, and number 2. You can choose to do them in this order or whatever order you wish to do them. 1, 3, and 2.